Hello, my name is Teppei Daito from Machine Learning Infrastructure team. In this session, I will introduce an RPC developed for machine learning. In the machine learning room, we use Kubernetes to secure the necessary number of GPU and CPU nodes and communicate with each other to perform machine learning. Machine learning jobs run on multiple nodes and communicate with each other. The CPU nodes fetch data from the storage and process it appropriately. Then the data is sent to the CPU node according to the learning requirements. In Kubernetes, pods can have access credentials for the storage using secret. This allows you to separate access credentials from the source code management. Limiting CPU and memory resources and collecting and reading logs from each pod are also important features. First, let's look at a simple example of a Kubernetes job definition. This is the job definition needed to display Hello World. I will select a few lines to explain. Since we can't throw a job with the same name, we'll add a random suffix so that we can run it multiple times. It is not convenient to retry the job from notebook or from the scheduler, so set all the job not to retry. This is a function to automatically delete a completed job after a specified time. If you don't set this function, the completed jobs will remain forever, and it will be very difficult to see them. This may not work depending on the Kubernetes version or configuration, so you need to check. Write the image and command to be executed. The upper limits for CPU and memory usage are set here. For the CPU, the OS will limit the allocated time, and we will not be able to use more than that. 1000 M is one thread of the CPU. In this example, the CPU usage will not exceed 20%. If you try to allocate more memory than the limit, out of memory will occur and the job will fail. That is all for setting. After that, you can save this file with an appropriate name and create it in kubectl and then view the pod logs to confirm that it works. If by any chance you fail, it would be good if you read events, since the cause of the failure would be known in many cases. Next, let's take a look at an example of actually throwing a job to the GPU along with a bash script to execute it. This is what happens when you try a combination of bash and YAML. You can use $brace to replace strings. In this example, image, command, and job name can be replaced. Naturally, you will have to create the image yourself, but there are many cases where you can start operation just by specifying the image and the command. This is the configuration for using the GPU. GPU nodes are few in number, so they are protected from running general jobs. You can also specify the GPU driver version and product name to run. With some modifications, almost every job will have such a setting attached. You can put the object storage credentials in secret and read it as an environment variable in the pod. From object storage, you can read the model and data and perform the calculation process. When I started using Kubernetes job using YAML and string substitution, the bash script got longer and longer as it ran, as shown here. Normally, It would be enough to create a job and read the log. But there is a reason why Bash script is so complicated. To retrieve and display the running logs, combine the wait command with the logs command. For example, the wait command can only wait for the pod to be in the running state. Therefore, it cannot detect completion, and if, for example, it completes before it starts and waits, or if an error occurs before it starts, it will keep waiting forever. On the other hand, the logs command will throw an error before the pod is running, so you need to wait for it to start. In other words, you can't simply wait and then log. You have to set a timeout and wait in a loop. The exit code may be 0 or 0.0 depending on the version. There are still many other problems, but at this point, it's time to give up. Maybe it's too late to give up. We have developed a command that addresses some of the points mentioned above, and we call it Swimmy. You don't need to write any Python code if you just start one pod and run the command. This is the most common usage, except for a few library developers, because they often just want to specify an image and execute one command. You can run any version of Kubernetes that supports job, and you can run it on any cluster without any prior preparation such as resident pods. Resource limitation is also possible. Since it is developed with low memory usage and short boot time in mind, it can be used for cluster management and image testing. Add environment variables. If you don't add values, the local environment variables will be transferred as it is. You can use the pod template feature. Information that is common to many pods can be saved as a template in advance and use it as a common settings for convenience. It is also used to prohibit local data access and to use Kubernetes secret. If multiple templates are specified, they will be merged if necessary. If there is an identical setting item, it will be overwritten by the later settings. Since there are multiple clusters depending on the usage and SLA, you can absorb cluster-specific differences by placing templates in config map. For example, the CPU in cluster A and GPU in cluster B can be used in the same way even if they have different settings and drivers. Since those settings are often common across jobs, it is reasonable to have them located in a cluster. Since arbitrary files can be sent, you can create a generic image and send the command you want to execute to it for execution, thereby reducing the time and effort required to create an image each time and improving development efficiency. If you are unable to start the program before the specified time, or if it gets stuck in the middle of the process, you can combine a function that will automatically fail if the specified time is exceeded after the execution starts. The only restriction is that the image must have the same version of Python as the driver. The agent will automatically gather the necessary libraries, so you don't need to worry about it. Even though it is automatic, it also focuses on low dependency, so if image is not too heavy, it will start up in few seconds. If you have multiple pods, you need to write the code in Python, as there are few cases that can be covered by just the Swimmy CMD. There is also an even bigger advantage to writing in Python. In an interactive environment such as Jupyter, you can send a file or function that you just wrote to run in an interactive environment while the pod is running and continue development. From here on, let's talk about the internals. The process in which this program is executed is called driver. The driver reads the pod specs, replaces it with the job information for Kubernetes, and asks the API server to create it. Of course, you can also use template and config map, which I explained earlier. There are more configurable items if you write them in code. The API server will create a job as specified and then create as many pods as specified in the job. If the pod has Swimmy in its image at startup, it will use it. If not, retrieve Swimmy and dependent libraries from the internal repository and start the Swimmy agent. Since the only libraries used on the agent side are ZMQ, serialize, and encryption, it is easy to avoid dependency hell. We have suppressed our desire to add useful features such as Hadoop support. We have had multiple Hadoop clusters in the past, updated, migrated, etc., and each time we did so, we updated the client. If you are tied to a specific version, you will be forced to upgrade in areas other than functionality. It is a good practice to keep it small in order to keep the environment and features separate. Likewise, there are multiple Kubernetes for different purposes, which also need to be updated more frequently. In a multi-tenant environment, for example, there is a great advantage in configuring only pure Kubernetes functionality, as it cannot be customized. Before creating the job, the driver should set up a server with ZMQ and embed a URL that can be read from the pod size as an environment variable. The launched agent will connect to the server built on the driver, and communication will be established. From this point on, the driver will be able to operate the agent freely. When developing the machine learning library, we considered several methods for transferring data between nodes. I've been using ZMQ because it's fast enough and because I can fine-tune the write buffer and other settings for transferring a large amount of data. Swimmy has also adopted this knowledge. Since the result of each RPC are returned in random order, async I/O and ZMQ are combined in order to process them efficiently. If a file is specified here, it needs to be sent to the agent. So, the driver will now build an HTTP server. Make the specified file a directory to be compressed and retrieved from the agent. The retrieved file will have the Python path through it, so it can be easily imported in the code. One of the important functions is health check. By periodically communicating from the driver side, the driver will know that the agent is alive, and the agent will also know that the driver is alive. If the health check fails consecutively, the driver will terminate abnormally. Also, the agent will terminate abnormally if it does not receive the health check for a certain period of time. Since the program terminates abnormally instead of deleting, it is clear how far it has been executed, making it easier to debug. Kubernetes job has a feature called active deadline seconds. This is a feature that Kubernetes stops the job if it has been running longer than the specified time. If the first health check is successful, extend the active deadline seconds. The reason why we take this approach is that there is no way to stop the job except by deleting the job if the driver fails before the connection is established by ZMQ. Initially, set it to the same time as the connection timeout so that it will be automatically terminated if the startup fails. Pod logging can be done as asynchronously and output as a log along with the agent's pod name. In the example of code, this would be output to standard error. The log level is info, so you may want to set up your logger appropriately. Events and other warnings of abnormal systems are output as warning. Now we can finally send arbitrary functions. Here we are sending a function to one of the agents. It is possible to send either an async function or both. It is possible to send the same function to all agents or to pass a list and pass different parameters to all agents. When execution is complete, as the title suggests, you should see Hello Swimmy. If there is a problem with the execution, you will be prompted to solve it. Here are a few examples. GI, the machine learning library used in-house, runs on Swimmy. For machine learning, we use a faster and more versatile communication library, such as MPI for data transfer between pods. Swimmy was developed with the stance that it would be easy to start a pod and leave the internal implementation to a dedicated library, thus maintaining the ease of use. We are also developing a machine learning API that launches a pod from Swimmy when a request is made to run a computational process, and an offline testing framework that uses many nodes. When scanning hundreds of millions of keys from Redis cluster consists of dozens of units, it would have taken an hour if simply executed from a SYN client. But by preparing the same number of agents as the connection targets and accessing them simultaneously, it was possible to complete the process in 5 minutes. That's 10-fold increase in speed. You can leak arbitrary load tools with scenarios you wrote yourself by running them on multiple nodes. For example, to provide a high load, you can set up several groups of pods for dedicated tools to load the target. At that time, you can check if the process is working properly by sequentially authenticating, updating, and checking the values from another group of pods. There can be routine in a single script, which allows for flexible test improvement. It is now an indispensable library when you want to run something on Kubernetes. I explained how to run jobs in Kubernetes and useful libraries for that. This is especially useful when you have separate Kubernetes clusters for different purposes. Also, by running the same code for notebooks and batch processing, we are able to increase the development speed. That's all for my presentation. Thank you very much.